Imagine for a second that you are tasked with building a massive, impenetrable digital fortress.
Right, a really big one.
Exactly. And this fortress needs to hold the most critical data for thousands of different people. It has to span the entire globe, and it absolutely cannot fail, even if, a physical fire wipes out a whole section of it.
Yeah, which happens more often than people think.
It really does. So that is essentially what enterprise cloud storage is all about today. And if you are joining us for this deep dive, you already know that mastering how to build and protect that fortress is, well, it's no small feat.
Absolutely not. It takes some serious technical grounding.
Right. So we are jumping straight into the architecture, the networking, and the sheer mechanics of passing the Dell exam, specifically the one pronounced D-ECS-DS-23.
It is a formidable exam, for sure. But it's a highly logical one once we break down the underlying principles.
Which is exactly what we are here to do.
Exactly. So the source material divides the DECS-DS-23 system into 5 balanced pillars. You have platform architecture, networking, data management, cluster access, and finally, monitoring and performance.
And each of those is worth exactly 20%.
You got it. Each of those holds equal weight. So our mission today is to logically dissect 10 core scenarios from the practice exam material.
We are going to go one by one, right through them.
Right. We are going to explore the mechanisms of these systems to understand exactly why certain architectural decisions are mandatory and why other seemingly good ideas will actually break your system.
Okay, let's unpack this, because before you can build out a massive storage system, you have to figure out how to divide the space for all your different users.
You got the multi-tenancy problem.
Exactly. So the material poses this first major hurdle. Let me just read question 1 in its entirety. It says, in a multi-tenant ECS architecture, how do you ensure the logical separation of management administrative boundaries between different business units?
Then what are the options they give us?
So option A is creating separate virtual local area networks, or VLANs, for each unit. Option B is deploying dedicated physical storage nodes. Option C is assigning a single shared access key. And option D is assigning dedicated namespace administrators.
Right. So my first instinct, well, maybe someone's first instinct to keep marketing away from finance data might be those VLANs or dedicated nodes.
Right. Just physically separate them.
Exactly. But following those instincts would lead to some major architectural problems. Deploying dedicated physical storage nodes, that's option B, it completely defeats the core purpose of a shared infrastructure.
Because you're just buying redundant hardware for everyone.
Right. It's incredibly inefficient. And using VLANs, option A, that is applying a network-level physical separation when the scenario specifically requires a logical management boundary.
Ah, I see. And C, a single shared key, I mean, that just sounds like a security nightmare.
A nightmare is putting it mildly. That would compromise the entire system. So the actual correct answer is assigning dedicated namespace administrators to each business unit.
So namespaces are the key to logical multi-tenancy.
They are. Think of a namespace as an entirely independent administrative domain living inside the system.
Okay.
By giving a business unit its own dedicated namespace administrator, that unit gets full autonomous control over its own users, its buckets, its policies, and it does all of this without affecting anyone else.
While still sharing the exact same physical hardware.
Exactly. It ensures strict logical isolation.
I like to picture an apartment building for this. The physical server is the building itself. You don't build a separate building for every single tenant.
Right, which would be the dedicated nodes idea.
Right. Instead, the namespaces are the individual apartments. Everyone shares the building's foundation, the power lines, the plumbing. But every apartment has its own lock, and the tenant inside controls who gets a key.
That is a perfect analogy. And extending that apartment analogy, once those logical boundaries and locks are established, the next architectural challenge is managing the actual plumbing, the data flowing through the network pathways.
Right, which brings us to securing those physical pathways. So let's look at question 3 from the source.
Let's hear it.
Question 3 asks, for network separation within an ECS cluster, which 3 distinct traffic types are typically isolated to enhance both security and performance? And the options are A, management traffic, B, data traffic, C, replication traffic, D, heartbeat traffic, and E, archival traffic.
Okay, so the 3 you absolutely must isolate are A, management, B, data, and C, replication traffic.
Just those 3?
Yes, those 3. This is a non-negotiable best practice in network segmentation. By carving out independent network paths for these 3, you ensure that a system administrator logging in, which management traffic, isn't competing for bandwidth with a client uploading a massive video file.
Which would be the data traffic.
Exactly. And crucially, neither of those should be able to interfere with the background internode synchronization. That's the replication traffic.
Right, that makes sense. Isolating them reduces bottlenecks.
Yes, and it closes off unauthorized access paths between the public-facing side and the internal backend.
Wait, I have to push back slightly here. The material mentions heartbeat traffic as option D. Isn't heartbeat traffic, those little signals nodes send to say, I am still alive? Isn't that critical for the cluster to function?
Oh, heartbeat traffic is absolutely vital. If a node stops sending a heartbeat, the cluster assumes it failed and takes action.
So why wouldn't we give that its own isolated tier?
Well, we have to look at the mechanism of the network. Heartbeat packets are microscopic in size. They really don't require the heavy-duty, dedicated physical network isolation that massive data input-output or continuous replication requires.
Oh, I see. It would be overkill.
Exactly.
Yeah.
Creating a completely separate dedicated network tier just for heartbeats would be over-engineering. The goal is isolating the heavy workloads from the sensitive administrative layers.
And what about E, the archival traffic?
That simply isn't a standard recognized network isolation tier in this specific architecture.
Okay, that distinction makes perfect sense. Keep the heavy lifters, the admins, and the internal syncing completely out of each other's way.
Precisely.
So we have secured the network. But let's look at a scenario where a compliance auditor knocks on your door demanding that 3 years of financial records remain absolutely untouched.
A very real-world scenario.
Yes. So this is question 4. It says, to ensure financial records cannot be modified or deleted before a specific retention period expires, which feature must be utilized?
And our choices.
Option A is server-side encryption. Option B is access control lists. Option C is role-based access control. And option D is object lock.
Okay, well, my mind immediately goes to things like encryption or strict access controls for security.
Right, that's what I would think.
Those are fundamental security tools, but they fail the compliance test. Server-side encryption, option A, scrambles the data so someone snooping can't read it. But encryption does nothing to stop a command to delete the file.
Right, if you delete an encrypted file, it is still gone.
Exactly. As for options B and C, access control lists and role-based access control, those are just software permission systems. A rogue administrator with root-level access could simply override those permissions and wipe the data.
So it has to be D.
Yes. To achieve true compliance, you have to use object lock. If we connect this to the bigger picture, this is all about strict regulatory compliance.
Let's explore how that actually works under the hood, because I think people hear object lock and just imagine digital superglue without really understanding the mechanics.
Yeah, that happens a lot. The underlying mechanism here is worm behavior. Write once, read many. Object lock doesn't just ask nicely. It writes a physical retention flag into the metadata of the object itself.
Oh, wow.
And that flag is enforced at the storage operating system layer. It essentially tells the storage controller, do not process any modification or deletion requests for this specific object ID until this exact Unix timestamp is reached.
So the system clock becomes the ultimate authority.
Exactly. Even a top-level administrator cannot bypass the storage controller's clock to delete the file. The power to destroy the data is mathematically removed from human hands.
That is fascinating. But, taking it out of human control doesn't save us from the laws of physics.
Sad but true.
Right. What if a hard drive simply catches fire? The data might be locked from tampering, but physical hardware still fails.
It definitely does.
This brings us to question 5. It asks, what are 2 specific mechanisms used by the system to protect data against hardware failures within a single site?
Okay, 2 mechanisms.
Yes. The options are A, erasure coding, B, synchronous external tape backup, C, file-level continuous data protection, and D, triple mirroring.
Well, we can immediately discard B and C, external
Okay.
tape backup and file-level continuous data protection.
Why is that?
While those exist in general IT, they are completely outside the scope of the native, built-in architectural mechanisms the system uses for intra-site resilience.
So that leaves A and D.
Right. The 2 native mechanisms at play here are erasure coding and triple mirroring. Triple mirroring, option D, is exactly what it sounds like. It creates 3 full identical copies of your data across different nodes.
Which sounds safe, but very heavy.
It is. It consumes a massive amount of physical storage space.
Right.
But if a drive burns out, recovery is instantaneous because you just switch to a perfect duplicate.
In erasure coding, option A is the more sophisticated alternative, right?
Yeah.
How does that math actually rebuild lost data without having a full copy?
It relies on parity math. To oversimplify it, imagine you have the numbers 5 and 3. You add them together to get 8.
Okay, I'm following.
The system takes your data, the 5 and the 3, and the parity piece, the 8, and stores them all in completely different drives. If the drive holding the 3 catches fire, the system looks at the remaining drives holding the 5 and the 8, does the reverse math, and instantly deduces that the missing piece was a 3.
Oh, that's brilliant.
Yeah. Erasure coding fragments your files, calculates those parity pieces, and spreads them out. It provides incredible resilience with far less physical storage overhead than just making 3 full copies.
Okay, here's where it gets really interesting. We have built an incredibly resilient single site using that math. Now we need to scale globally by connecting multiple data centers together.
Time for federation.
Exactly. Question 7 explores this. It asks, what are 2 core benefits of federating geographically dispersed virtual data centers?
Let's hear the options.
Option A is the complete elimination of network latency. Option B is centralized management. Option C is automatic protocol translation. And option D is enhanced data availability through cross-site replication.
Well, federation transforms separate physical sites into one logical powerhouse. The 2 major benefits you gain here are B, centralized management, and D, enhanced data availability through cross-site replication.
Can you break those down?
Sure. Centralized management allows a global administrator to oversee distributed data from a single pane of glass. And cross-site replication is your ultimate disaster insurance.
Right.
If a massive power grid failure takes your entire primary data center offline, your data survives because it has been replicated to other geographic locations within the federation.
And I assume we can safely laugh off option A, the complete elimination of network latency.
Oh, absolutely.
I mean, unless someone has secretly defied the laws of physics and invented faster than light travel, transmitting data thousands of miles will always involve some latency.
Always. You can't beat physics. And while option C, automatic translation of file protocols to object protocols, is a real feature in some gateways, it is not the core architectural driver for federating entire data centers.
Got it. So that brings up the immediate next problem. Once you federate these sites globally, you have to manage the traffic.
Right.
Which leads us to question 2. When implementing global server load balancing across this federated environment, how does the system direct client read requests most efficiently?
Okay, what are our choices here?
Option A is routing traffic to the site with the lowest storage utilization. Option B is forwarding traffic to the site where the data is geographically owned. Option C is distributing traffic evenly across all nodes. And option D is using a round-robin distribution.
The only viable design requirement here is B, forwarding traffic to the site where the requested data is geographically owned.
Why just that one?
The entire architecture is governed by data locality. If you use round-robin option D, or even distribution option C, you are essentially playing roulette with geography.
How so?
Imagine a user in Tokyo requesting a file. If the load balancer uses round-robin and happens to hand that request to a node in London, but the authoritative data physically lives in New York, the system has to haul that data across the wide area network, across multiple oceans.
Oh, wow, the latency would ruin the user experience entirely.
Completely ruin it. And routing by lowest storage, option A would do the exact same thing. It just arbitrarily sends you somewhere based on disk space, not where your data actually lives.
You know, it is exactly like ordering a library book.
Yeah.
You wouldn't ask the library system to ship a copy of a book from a branch 3 states away if there is a perfectly good copy sitting right in your local town branch. You route the request to where the book physically lives.
That is spot on.
But what if a law dictates that the book is so sensitive it legally cannot leave that local branch, even in a global system?
Ah, data residency.
Yes. Question 6 presents this exact scenario. A customer requires certain sensitive objects to remain physically located only at the primary site while still being visible in the global namespace. How is this achieved?
And the options.
Option A, implementing replication group restrictions on the specific bucket. Option B is disabling the global load balancing feature. Option C is storing the objects in a disconnected namespace. And option D is configuring client applications to encrypt the data before upload.
This is a classic data residency challenge.
Yeah.
It's often driven by international privacy laws dictating that citizen data just cannot cross national borders.
Right.
The configuration that solves this is option A, implementing replication group restrictions on the specific bucket.
How does that work in practice?
By applying a rule at the bucket level, you command the system to halt physical replication for those specific objects. They are never copied to the secondary sites. But Because that bucket is still part of the federated architecture, its metadata remains visible globally.
So it physically stays put, but logically, everyone in the global system knows it exists.
Exactly. That perfectly satisfies the requirement.
And if we look at the other options, disabling the global load balancing feature, option B doesn't actually stop the backend system from replicating the files behind the scenes.
Nope, the background sync would just keep running.
And storing the objects in a disconnected namespace, option C completely violates the requirement that they remain globally visible.
Right, because it's disconnected.
And configuring client applications to encrypt the data before upload, option D, entirely misses the point. You would just be illegally sending encrypted data across borders instead of unencrypted data.
Exactly. The legal framework doesn't care if the data is encrypted. It cares where the server is physically bolted to the floor.
Good point. Now, understanding how data is distributed and restricted helps us answer the next critical design question. How much hardware do we actually need to buy?
Sizing for high availability.
Yes. Question 8. When designing a multi-site deployment with varying workloads, what is the primary factor that determines the minimum required storage nodes per site?
Let's see the options.
Is it A, the specific erasure coding scheme selected, B, the geographical distance between sites, C, the number of Active Directory users, or D, the load balancing mechanism?
Okay, the mathematical foundation of your hardware is dictated by A, the specific erasure coding scheme selected.
Going back to the math we discussed earlier.
Exactly. We talked about how erasure coding fragments data and parity. Well, if you choose a scheme that splits a file into 12 data chunks and 4 parity chunks, the system physically requires enough separate node to distribute those 16 pieces safely.
Oh, I see.
That coding scheme establishes the absolute, non-negotiable minimum number of physical nodes you must purchase and rack to tolerate a failure. It is the mathematical floor of your architecture.
I love that phrase, the mathematical floor. Because the geographical distance between sites, option B, might force you to buy faster network links.
True.
And the number of users, option C, might require better identity management. And the load balancer, option D, handles traffic flow. But absolutely none of those factors mandate the minimum physical hard drive counts for high availability. Only the math of the erasure coding scheme does that.
The math writes the rules. But let's say you follow the math, you build the perfect cluster, and a year later, the business is booming.
A good problem to have.
Right. You need to expand. You want to add new nodes to meet capacity demands. What architectural constraint must the design adhere to?
Okay, that is question 9. The material gives us a few constraints to evaluate. Option A, new nodes must contain a smaller storage capacity. Option B, the expansion requires a completely separate physical rack. Option C, the cluster must have a minimum number of contiguous network addresses available. Or option D, all existing nodes must be temporarily powered down.
The definitive constraint here is option C, the requirement for a minimum number of contiguous network addresses.
Why is that so strict?
When you introduce a new node to the cluster, it isn't just a dumb hard drive. It is an active participant that needs to run internal services, like chunk management, object indexing, and back-end routing.
Okay.
To assign these services, the system relies on a pre-allocated internal subnet. It mathematically slices up a block of IPs. If you try to hand it a fragmented random set of IP addresses, its internal routing logic breaks down. It physically cannot assign the services to bring the node online.
You know, I have to admit, this one surprised me.
Yeah.
In an era of advanced cloud architecture, artificial intelligence, and globally federated systems, the ultimate bottleneck to physically plugging in a new server is something as old school as running out of sequential IP addresses on a subnet.
It is a bit ironic, isn't it?
It really highlights how critical foundational network planning is. And looking at the other options, forcing smaller capacity nodes, option A is totally counterintuitive to scaling up.
Absolutely. You usually want bigger nodes when you scale.
And forcing a completely separate physical rack. Option B is an arbitrary physical rule, not a system constraint. And option D, powering down all existing nodes. I mean, that would trigger a catastrophic outage and ruin the high availability we just spent this entire deep dive designing.
Shutting down the cluster to upgrade it is the ultimate architectural sin. The system is designed to expand dynamically, provided you have those IP addresses mapped out.
Okay. We are in the final stretch. You have successfully expanded the cluster, the IP addresses are flowing perfectly, but suddenly, system performance completely tanks.
Oh, no.
Yeah. This is our final question, question 10. A bottleneck is suspected because users are suddenly uploading millions of tiny files. Which component is most likely experiencing exhaustion under this specific workload of intensive small object writes?
And our options are,
Option A is network bandwidth. Option B is read cache memory. Option C is solid-state drive capacity utilized for indexing and metadata. And option D is central processing unit resources allocated for read operations.
the component collapsing under that pressure is C, the solid-state drive capacity utilized for indexing and metadata.
Why the SSDs specifically?
What's fascinating here is that the key to understanding this is the payload to metadata ratio.
Let's break that ratio down.
Okay, when you write a massive 10 GB video file, the system records a few kilobytes of metadata. You know, who created it, the timestamp where it lives on the disk.
Correct.
The SSD barely breaks a sweat logging that index, while the spinning drives handle the heavy video payload. But if you upload 1 million 1 KB text files, the payload is tiny, but the system still has to generate, process, and write the metadata for every single one of those million files.
Oh, I see. The ratio completely flips.
Exactly. The system is suddenly generating a massive storm of indexing operations, and all of that metadata has to be written to the solid-state drives. The input-output operations per second, the IOPS on those SSDs, become completely saturated.
So what does this all mean? It means you have to map the hardware bottleneck directly to the specific nature of the data.
Precisely.
Millions of tiny text files do not consume massive network bandwidth, which immediately rules out option A, network exhaustion. And the problem clearly specifies intensive small object writes, so we can completely ignore read cache memory option B and read CPU resources option D.
Right, because you cannot blame a read component for a write workload bottleneck.
Exactly. So the SSDs are simply drowning in index paperwork.
That is the perfect way to summarize it. The system isn't out of space. It is just out of administrative bandwidth at the disk level.
Thank you so much for joining us as we take this deep dive into the DECS-DS-23 exam material. Keep questioning how the underlying math works, and we will catch you next time.